everybody to my presentation on Fullstack Quantum Compilation, Minding the Pulse Gap. My name is Doris Bailey. I'm team lead here at Quantum Machines. So let's begin. Okay, so what do we do at Quantum Machines? We have the Quantum Orchestration Platform, which is an integrated hardware and software solution. On the one hand, letting us control via pulses, RF and microwave, the physical systems. And on the other hand, using a very sophisticated and advanced dedicated pulse processor, we have very advanced capabilities, waveform generation and acquisition. We have real-time functions and mathematics. We have, again, real-time control flows, conditionals and loops. Everything is enabled, obviously, for all of the qubits or all of the quantum elements. And it is exposed to the user via intuitive quantum programming language, an open source language, by the way, called Quad, that we have created, that abstracts away all of the compilation and the hardware, thus letting us serve almost 100 users globally, ranging from all types of qubits, from superconducting and trapped ions called atoms, envy centers, what have you, we have it. Okay, so the QP, or Quantum Orchestration Platform, as I mentioned earlier, allows users to do research, characterization, calibrations, quantum sensing and communications, and recently even we've demonstrated quantum error correction algorithms. And now we implemented quantum computing algorithms, which is very nice. We implemented all of the above using our Pythonic pulse level language QA, and it's very efficient, it's very elegant, but we want to enable quantum computing algorithms to be created and integrated via high-level languages, via their go-to reasoning languages, which is the circuit model. So what is the circuit model? The circuit model is a computational model for quantum algorithms or quantum computing. It's equivalent to the quantum Turing machine computation model. The difference is that is a visual and very elegant model. It's written in gate-level languages like IBM's Qiskit, Google Cirq, and it has gates and measurements that you can apply on given qubits. The qubits don't disappear, they are not added. You start with 5 qubits, you end up with 5 qubits, and you can only apply one gate on each qubit at a time. So you cannot do, for example, an Hadamard gate and also an X gate simultaneously. You need to order them one after the other. This abstraction is very nice and it's very popular due to the fact that it allows us to focus on the algorithm itself, on the mathematical side, mathematical aspect, and ignore the hardware and the timing constraints. So it's hardware agnostic, right? It doesn't concern itself with the type of qubits or the number of cables, for example, and it's also time agnostic. It doesn't care about how long does it take to apply an operation. It only concerns itself with the order of gates. And we want to enable this on the QOP. So we want to allow users to write and reason about and integrate with these high-level languages, these gate-level languages, such that our solution, the QOP, will understand the gate-level instructions and will control via pulses the qubits. We want to support or to keep supporting all of the QPU systems, right? So we have, again, superconducting and color atoms and all of that, such that the QPU vendors will only need to configure their specific setups. They won't need to recreate all of the solution. This is very nice, but it requires compilation from gate level to pulse level. Why? Why do we need compilation? Why do we need quantum compilation? So for two reasons. The first one, functionality. So control systems don't understand our mathematical abstractions. Gates and circuits are a mathematical abstraction which is not understood. What is actually being applied are pulses, right? So we need to somehow translate or compile down those mathematical abstractions into pulse instructions. The second reason is optimization, meaning the act of taking one circuit, one quantum program, and making it better, more optimized in some manner, for example, the depth of the circuit. This is a must for the NISQ era, as the qubits are short-lived and with low fidelities. And there are companies doing specifically this, as it's such a tough problem. So what are the challenges that we face in quantum compilation? Firstly, hardware agnostic challenges. Secondly, the hardware dependent challenges. For example, let's go over the flow. So you have some problem, right? We formalize our problem using equations, Hamiltonians, for example. The first challenge is to synthesize the equivalent quantum program or quantum circuit that solves the problem at hand. Secondly, you want to optimize the circuit, right, to make it shorter, for example. Now, given some specific hardware and qubits and control system and so on, you might need to translate some of the gates to the natively supported gates, right? But then maybe you need to re-optimize the gate. Thirdly, we need to take into account the connectivity of the qubits. Maybe not all of the qubits are connected, which is the most common case, and we need to add swaps. We need to route qubits around. Then, in order to execute the result, we need to schedule the gates, which again don't have to have the same duration, right? Maybe X on qubit 1 and qubit 2 are not of the same length. We need to schedule them relatively one to another. And finally, as I mentioned earlier, we need to translate all of the gates to their equivalent pulses, which might be several pulses to one single gate. Great. So are we done? Is that all? Well, yes and no. Yes, because the most basic algorithms or toy problems can be solved using solving those challenges, but this is not enough, and this is the essence of my presentation. This is not enough for next-gen quantum programs. For example, the most basic example is quantum teleportation, right? So everybody learns quantum teleportation. We have some gates, and then if you think about it, we have measurements in the middle of the circuit, and quantum bits don't live in most QPU types. They are short-lived, right? So how can we do mid-circuit measurements? How can we do real-time conditionals without ruining the qubit state? This requires to improve our model and our formalization. Also reset operation, right? So in most algorithms, we want to initialize the qubits to the 0 state, or maybe even in middle of the circuit, like in an example I will show shortly. We can't just wait some amount of nanoseconds as a function of t1, because firstly, it's not exposed in the circuit model. Secondly, it's not efficient, right? And thirdly, it doesn't even promise you that it will be initialized, right? It's a statistical number. Okay, so you might say, let's measure the qubit, let's add mid-circuit measurements and real-time conditionals. Measure the qubit. If it's excited, do an X gate. If it's not, just do the identity gate. But again, this assumes that the X gate is perfect, which is not, right? So you would like to do something like this. You would want to have some non-deterministic while loop that while the qubit is excited, do an X gate and measure it again, right? So suddenly now we need classical bits to store the information. Suddenly the scheduling is non-deterministic. It depends on the measurement result. A more recent example is by Honeywell by 2021. We won't go into detail, but if you zoom in on this specific part, you can see, again, mid-circuit measurements, conditionals, and in this condition, we have change in syndrome, which means we need to first remember what the syndrome was, so we need memory, and then we need to check for changes. We need some real-time logic, arithmetics. IBM coined the notion of dynamic circuits in their OpenQASM 3 language. OpenQASM 3 is the next generation quantum assembly language. It's a multi-level intermediate representation language, meaning that it formalizes both the abstract circuit down to the most physical calibration, accessible through the conventional circuit model. It has both the high-level construct that we talked about, the mid-circuit measurement, for example, subroutine, real-time functions, and also some hardware-aware imperatives, for example, timing, which again, the circuit model doesn't concern itself with. This will become the go-to reasoning for Qiskit, and I'm sure more will follow as they adopted OpenQASM 2. So this is an example from IBM's 2021 paper on iterative quantum phase estimation. It doesn't really matter the details of the algorithm, but we can see they have reset operation, we have mid-circuit measurements, we have real-time conditionals, right? So this is the OpenQASM free code, and in red you can see the real-time variables, the reset operation, the for loop, the mid-circuit measurement, right? And the real-time operation. We need somehow to support all of that. So suddenly we have very new compilation challenges. We have classical compilation challenges that rise from the new variables and the new for loops and so on. Okay, for example, you have basic blocks suddenly. We didn't have that before. Before the circuit was just a linear program, right? Now it has conditionals, it has for loops. We have loops, so we need to optimize them, right? You cannot just unroll all of the loops. It will cause a program length blow up, right? You might do that for 3 or 10 or even a few dozen qubits, but it doesn't scale up for thousands or maybe millions, right? And also it gives rise to quantum-specific compilation challenges that we haven't faced before. For example, the classical logic, the conditionals, right, the variables, the calculations take time. Qua handles that. Qua support real-time logic, Qua handles gaps, and we have all of those high-level constructs. For example, we have the plane measure, obviously. We can have variables and real-time calculations. We can use those real-time calculations and variables in the pulses. We can control the amplitude or the duration or frequency and so on. We can do very advanced measurement schemes. We can do some integration and according to some calculation, the result define, understand if the qubit was excited or not. Obviously, we added conditions and while loops and so on. We give user the ability to have absolute timing control, both absolute and relative timing control, sorry. In summary, next-gen application requires real-time logic. There's no escaping from it. The quantum field is ever-changing. We must have agile foundations. We cannot be stuck whenever some new language needs some new feature or some new algorithm needs some new construct, right? We need to take that into account. And thirdly, there are a lot of quantum applications, and we see that daily with our customers. We need one-stop solution which is efficient and generic that can handle all of those different use cases. So thank you very much. We have more talks in the coming days. We are at booth 609, so if you have questions, either ask me now or come visit us. We have also some cool demos, and thank you very much.